Recordings beginning now. Well, thanks everyone for joining me here for another session, our online web-based seminars. Today we're going to get an opportunity to switch gears and go back to turning, and we're going to be working with advanced cycles, specifically to ShopTurn. So it's going to be all conversational-based programming, but we will be looking at some of the more either advanced cycles or features or functions that I think get commonly overlooked that can certainly add a lot of power and capability to the control. For those of you that may not know me yet, my name is Chris Pollack. I am a dealer support specialist for Siemens based on the East Coast of the United States. I currently cover from Maine to Florida, and I interface with dealers, OEMs, importers, really anybody bringing Siemens-equipped product into the U.S. and selling it in the machine tool market. I am certainly a resource for you, whether you're in my territory or outside of my territory, and you can always get a hold of me either via my phone number or probably even easier would be my email address. And if you need to, I can always give you a referral to a local rep. We have multiple people positioned throughout the United States and actually throughout the world doing my position as well. So up and coming, with this being towards the end of the year, I'm kind of refilling the kitty, so to speak, on some of the seminars coming up. I'm going to continue to try to do this program about every 6 weeks or so is roughly what we try to run one of these events on. So certainly I think the next one's going to be a good one. It's certainly brand new content for us, and that's working with the DXF converter. So we're going to get a chance to take a look at that, using it for both shop mill, conversational programming, and program guide. Not sure if we'll do a turning example yet. We'll kind of have to play around with it a little bit. But either way, it would apply for turning or milling the process of events using DXF. So we are going to get a chance to see that. That's going to be coming up this January. Just want to, again, as I have in past webinars, just mention our core websites here. Certainly you have the main website, which is our CNC for You. The top address you have across your screen will get you to our main landing page. From there, you can access the webinars, or you can go directly to our webinars through the link just below. And there, if maybe you haven't actually been to our site, or this is your first time viewing one of the webinars, here is where not only you can see what's coming up, and you can register for the next event, certainly, but you can also see all the past recordings as well. So if for some reason maybe you want to refer this out, or you just had missed one, you can always go to this website. We're keeping all of the webinars here posted for your viewing purposes. So today's webinar is going to be specifically concentrating on both 840 and 828. So all of the functionality we talk about here will support either of the two controls. Now this is all based on what we call Operate, which is our current software system. So some of you may have older versions of the control. You might find some slight differences, but I would say probably 95% of everything I show you today, although it might look slightly different, could be leveraged even in the older system. We've had a lot of this functionality for quite some time. But again, everything I'll show you is on the current Operate system, which is our latest software version. So today's course, we're going to kind of get right into the meat, and I wanted to really take some of the things that we've maybe touched upon at high-level aspects and really kind of dig into them a little bit. So we are going to talk about creating tools, but we're going to really get into looking at the full geometry of a tool. What are all the critical parameters of the insert insert configuration and the holder configuration, and how does that affect the ending result cutter path? So we're going to really dig into really the makeup of tooling and turning. Turning can get pretty complex when it gets to the turning, the tooling side. From there, we're going to get into contour turning, but specifically contours with pockets, like irregular shapes, like hourglass style shapes. This way you can start to see how that geometry becomes so critical when I send tools into areas that maybe don't fit. And we can see the gouge detection, and then from there we'll certainly play around with an option called residual material detection. You'll get a chance to see that. There are certainly a few unique strategies for handling whether it's chip handling scenarios or just increasing insert life that we're going to talk about. Then we're going to work with pre-machined or pre-cast blanks, so irregular stock, instead of machining everything from a bar stock, which is what we have a tendency to obviously do quite often. And then from there, we're going to look at the contour grooving and plunge turning cycles as well in the control. So the first area I wanted to concentrate on, and we're going to jump right into, is kind of tool setup and geometry. When I say tool setup, I'm not talking about, set X, set Z, measure tool. I'm talking about creating the tools and what's the geometry involved with it. If you guys are maybe new to these webinars, certainly take a look at my webinar pages. I have some more basic webinars I've posted in the past that go through the basics of touching a tool off. But now we're going to start to talk about what makes turning so complex, and then how do we handle it. And here's a perfect example of all of the different types and configurations of tooling. And this is just showing you OD tools. This is barely even going into facing tools, and certainly not even showing you ID tools. So there's all kinds of different configurations of tools, and how these tools, physically fit. A lot of people think, well, I understand I have an 80-degree diamond. Well, that's great. We need to know that the tool has an 80-degree diamond insert, but we also need, almost more important, to know how it's physically sitting in the holder. And you can see here how many different orientations. So we're going to start to explore a lot of this over the next 15, 20 minutes at the beginning portion of the webinar. So as we start to get into this, probably the first and the most important thing to start understanding is knowing where your physical tool is in an orientation position. So is it in a right-hand orientation, a left-hand orientation, a neutral orientation? And then you have to describe that to the machine. It's one of the first things we kind of ask you. So I like to bring this up. Certainly, probably a lot of us are used to, anybody that's certainly run the control before, setting up a basic tool and telling it which way it's pointing. What a lot of guys don't realize is possibly, especially if you're kind of new to turning, how do I know if it's a right-handed tool or a left-handed tool? The industry itself calls out tooling based on right-handed or left-handed or neutral, meaning the tool's pointed in the middle. So what I want you to look at is I want you to look in the upper left-hand corner of this diagram. There's the P1 example with a little R and an L. And we want to specifically look at the R tool. And the R tool has the insert facing up or on top of the tool, as opposed to the tool being sitting upside down. So this is a quick little way for you, if you ever need to know what is the type of tool, what's the hand on the tool, is it a left-hand or right-hand tool. Take a tool, position it like it's sitting with the insert pointing towards your chest, and then look to see which arm or which hand is the insert pointing at. So in this example right here, you'll see that if I was holding this to my chest, that insert would be pointing to my right hand. This is how I know the system is, or the tool is a physical right-hand tool. If I had the tool and it was like the P2 with the L pointing at my chest and the insert's the other way, that's a left-handed tool. So when you're starting to create or build tools in our library, this is going to be the first thing you have to do, is you have to signify how the tool is physically sitting in. And you can see there's a whole bunch of different orientations. Handed tools, we can see on the right lower corner, neutral tools. So that's the first and most basic. We got to kind of tell it roughly where the tool is sitting. From there, you're now going to get into how does the insert physically sit in the holder. And you can see the same insert can be sitting in the exact, sitting in a holder all sorts of different ways in different orientations and different positions. Why we really need to know this, why it becomes so important, is because when you get into scenarios like we're going to look at later, where I'm creating like hourglass shapes and doing what we call like pocket turning, I need to know where the back side of this tool is. I need to know where the back side of the insert is. If I don't, and I send a tool into an area, like you see this little groove here, where it potentially can't fit, if we don't know where the back is, we could crash that tool, or we just wouldn't go in there at all. And what we want to do is we want to use as much of the tool as we possibly can when machining a part. So that's where this all comes into play. So we're going to start to explore how this physical tool sits in the pocket, and then where I feed that information within the standard description of a tool in our system. So what I've done for you here is I've drawn up 3 very common configurations of tools, but now we can start to look at and understand a little bit why the values are the way they are. So the first thing I see in this top left-hand tool, this is a standard 80-degree tool. I see it's 80 degrees, shows me with the occluded angle, and I would know, kind of being familiar with the shape of a tool. But what I see here is I see this 5-degree, this is what we call a relief angle. So that means that the physical pocket was machined in this holder to take that insert and rotate it off of 0, right off of this tangent face, 5 degrees, hence giving us a little relief. So if I was to send this tool up to the face of a part, I would have a little bit of relief on the insert so it's not dragging the whole insert up the face of the part. Now for us, this actually is going to be entered in as what we call the holder angle. And the holder angle is going to be the total distance from 0, or from this base plane, all the way to the relief angle. And the holder angle can be seen right down, if you look at the lower description where we have a value of 95, that represents your holder angle. So when inputting a value and getting the correct orientation of a tool, you want to use whatever they call out the relief angle to be plus, in this case, 90 degrees. Now the reason why we're coming off that base position is if you look at a simple neutral tool, we're still coming off the same base, but now that value for orienting that insert is actually less than 90. So here I would actually physically put in 72.5 degrees. Now when you get to button tools are a full profiling tool. So here we don't necessarily ask you to give us that relief angle because we expect it to be a full 90 degrees. Now what you do have to be careful of, although we are orienting the insert, we don't actually have a representation of the holder itself. So I still have to be careful, where the back of the holder is, like for argument's sake with this button tool, if I went beyond the center line of this insert, I could potentially clip the part with this holder. So that's where that's not up to you. There's always going to be a little responsibility on you, the operator programmer, and that's kind of the big area here. So that's how we first know where the insert is rotated in. Now the next thing to start to talk about is some of the critical values or dimensions of a specific insert. And what I wanted to do is I wanted to just give you an overall sampling of some of the more common inserts you're going to see in the industry. So certainly we have full 90-degree inserts, and that would be a straight square insert. We have the button tools like you saw before. And then we have a lot of different diamond configurations and triangular configurations and whatnot. So here I'm showing you a very common roughing tool, which would be an 80-degree diamond. And then I'm also showing you a 35-degree diamond, which is more traditionally used for finishing operations. So for us, there's 3 important values we ask you to input. We ask you to give us the tool radius. We see that that's the physical radius, and that'll be the same radius on all 4 corners of an insert. Inserts are symmetrical as far as that's concerned. I need to know the insert angle. That would be the included angle from cutting edge to cutting edge. And I also need to know what's called the LOC length, or length of cut of the insert. Now that's also in the industry referred to the IC diameter. And IC stands for inscribed circle. So what happens with the IC is if I was to draw a circle and the circle was tangent to my cutting edges, no matter what the shape of the insert is, and I measured the diameter of that circle I drew, that is the IC diameter, and that's what gauges the size of this insert. So when we look down on our lower field, the tool radius is going to feed into the radius field. The insert angle is going to feed just past the holder angle, and then the IC diameter is what's going to be inserted into the LOC length field. Now, just to give you guys a little bit more background on inserts and how they kind of work and where some of this data is really coming from, I wanted to show you what's the standard IC protocol or terminology, standard industry ISO protocol, shall we say, of an insert. And there is metric and inch, so you do have to be aware that there's going to be slight nuances or differences, so you want to make sure you're looking at the right one on the insert package. But what you're going to see is you're going to see a 4-letter designation, and then some numerical values, and then you may be, filling out or describing the chip breaker, coatings, insert grades, and all this stuff is spelled out within this part number, this unique number on this physical insert. So the first one, and I only picked out the ones that are directly relate to what you're entering in the fields, like we just showed you in the previous slide. But the first value here, or first index, is always going to refer to the shape of the insert. So that's when I see number 1, shape. Anytime there's a C designation, that is always going to be an 80-degree tool. If it has a D, it'll be a 55-degree tool. Let's say it's a 35, it'll physically have a V. So that's where we know. Whenever I look at and I say, oh, I got a DNMG 432, I immediately know the D, okay, I got a 55-degree insert. And that's how you can start to tell. I'm not going to go into a lot of detail on these others. A lot of it has to do with tolerancing of the insert, or what does the center hole look like, a bunch of different features. But the next one that's important for us is actually the 5th index, the 5th digit, and what that describes is the IC diameter I just talked about. So if I have a CNMG 432, a very popular insert that I would hear of a lot, the 4 in the 432, if looking at the chart, is signifying a 1/2-inch IC diameter. From there, 6, I'm pretty sure, if memory serves me, is directly to thickness. 7, however, is another important one we want to look at, and that's your corner radius. So if this, again, was a 432, I would look for the 2 field, and that would tell me, oh, I got a 1/32 or an 031 radius on that physical tool. And then I can build it from there. So to just kind of demonstrate that a little bit, I do want to jump over to Sinutrain. Sinutrain is that machine emulator, the virtual emulator that's going to mimic the physical control or machine under control. And I'm going to delete a couple tools, and we'll build a couple tools from scratch here. So I wanted to build certainly an OD tool, and we can go through and kind of feed the fields like we were just talking about, and maybe we'll build a neutral tool just to kind of go through it. Okay, so I'm going to select new tool and say find the field, just like we always would. And here's your orientation. So the first thing, you see the 4. Well, don't forget, I can expand this over. So if I have a neutral tool, I got to expand over to get to it. So there's actually 8 configurations of tool on each of these lines that I can support. We're going to pick the first position, always signifies an OD tool. So if you have a rear turret, it's going to look the way this machine looks. If it was a front turret, the picture would actually be backwards. It would look like the 3rd place, but the first position is always OD tools. Oh, I'm sorry. You guys aren't seeing the Sinutrain screen. I need to share it. I'm glad somebody just told that to me. All right. Give me 1 second. And we should all have it. Thank you for letting me know that. I caught that out of the corner of my eye. Okay. So we're here. We're building the tool, and I was just showing the 8 different orientations on any given tool. So when you pick that new tool, the first thing we're going to have to choose is the way it sits, and this first one is always going to signify an OD tool. From there, once you pick the appropriate tool orientation, simply hit OK, and now you get the option of giving it a name. So let's say I wanted to use more of that ISO standard for my name. I'm going to create a CNMG 432. Now, a 432 insert could exist in my OD, ID, and it's common to have ID. Remember, this portion is only just the insert. So a lot of times I will tell it maybe it's an OD tool. Maybe I even want to tell it it's a right-hand or a left-hand tool. I could put that as well, depending on how involved I'm getting into different orientations of tools. And you guys will kind of come up with what you feel like your own standard would be. So we give it a name. Certainly, we have our sister tool and our cutting edge to default, and we'll talk about cutting edges in a little bit. And then I want to come over to the radius. So to refer back to the previous slides, I have a 2 designation here. So if I come on back to my PowerPoint, and we just move back to the number 2 field, which I know now is the number 7 position. This is where I see my 1/32nd radius. So that's what I'm going to directly put into the radius field. We do support fractions here, so it'll do the math for me. Then we have our holder angle. So I would certainly need to know which of the holders I was creating, but maybe it is a pretty common 5-degree relief. So then I'm looking for a full value of 95 degrees here. Now, if I was in this previous slide, I would, this would be, this one in the center would be the one we're creating right now. It's a 95-degree relief angle for our tool. Now, we happen to default it to 95, so I can leave that alone. It was defaulted to 80, but I now know that the 80 is signifying by the C in the string, so I can type in my 80. And then the final question was the IC diameter. Remember, that's that inscribed circle. That goes off of the 4, which in this case, according to our chart, was a 1/2 inch. And now I have enough information to know where the tool is and kind of how it tracks and how it goes. And just to show you quickly, like if we were doing a neutral tool, like that 35-degree neutral we just showed before, I'd probably pick a finish because the insert picture looks a little bit more like it. But now I got to remember to expand over and pick the appropriate orientation. So I pick the neutral tool. I say OK. I'm going to call this, and maybe it's a VNMG, pretty common, like a 331. And we'll say that this is an OD tool as well. And maybe because there could be a handed tool, the same geometry, I'll even tell it it's a neutral tool. Okay. So the one field, if I was to jump back over to my chart here real quick, I look for the number 1, and I see that number 1 signifies a 1/64th radius. So again, that's what we're looking for right here. We're looking for my 1/64th. It's going to give me my 15-pound nose radius. Now my orientation angle, this was defaulted because we assumed you were building or just gave you a basic 55-degree. Since you're really giving a 35-degree, I want to put the insert angle. But look what happens now to this picture. The picture is really good when you're first getting your head around the value I put here. As you start to put different values in, you start to see it's going to rotate that tool. So I can see pretty quickly that it's not quite straight up and down. So referring back to that previous print, if I put my 72.5-degree angle in, my insert goes neutral. And my final 3 in the 331, this first 3, signifies a 3/8 IC. So we only show 1 decimal place here just for space purposes, but put your full 375. Even though it rounds it up to show 0.4, it's actually using 3s, so you can type in the full value. Okay, and that's how you start to leverage some of these more complex geometries or shapes, or at least why you're certainly filling out these fields. Now the next area I wanted to show you, which gets quite common in turning, is working with multiple cutting edges. So what we've shown here is a nice little standard flat bottom insert drill. And an insert drill works actually very well as a boring bar. So what I can actually do is I can use this leading edge insert right here that I see and create this to be a boring bar. But what happens is now I need 2 different offsets. I need an offset set up at the center of the tool, and I need an offset set up at this leading edge of this insert. So this is where it comes into what we call cutting edges. And that is what this whole D field right here is all about. In the Siemens control, you can set up a maximum of 9 different cutting edges for every tool you create, or 9 different unique offsets. Now, it's always physically the same tool. So whatever I name the first tool to be, when I create another cutting edge, it's always going to use that same name. But I can then change the entire type of the tool and try to completely recreate what the tool is going to be. It's just going to use a common name. And all of my length offsets, all are brand new. Radiuses, all that stuff become brand new based on the new configuration of the tool. So to give an example, we're going to actually take a look at a pre-machined part or pre-created, pre-programmed part where I've used the same tool to drill a hole and to and then immediately jump in and bore that hole. And we're just going to flip between those two. So we're going to look at that example, and we're going to get a chance to see kind of what makes it up. So first things first, I'd have to look at creating the tool. Now, I do happen to have a tool I think created here. Yes, I do. This is our solid drill. So I chose first the solid drill field because it doesn't make me put a tip angle in. I certainly could have used our traditional twist drill, which a lot of guys are probably already used to, but it asked me for the tip angle. And then I would have had to obviously fool the numbers to make it come out flat. So in this case, when you start to create new tools, right, start to explore some of these other buttons. So we always concentrate on this favorites tab, but there's all kinds of additional tools if I drill down. So when I go to drilling, there is a tool called solid drill. Now, if I don't want to or I want to use a twist drill, it's okay. You can change it so it thinks that the front of it's flat. This one just keeps me from having to do it. So I had picked that tool, and that created my first tool. I do need to give it a diameter because it's a drill, so I was saying that we were going to use a 750 tool. Now, when it comes time to create the new offset, and I can do this for any of my tools, you want to take a look at this Edges button. So when I go to Edges, I now can come in, and I can say I want to do a new cutting edge, and the system will automatically build you the cutting edge number 2. Now, you see there's no number here in the location. This is the same tool. If I remove it, if I unload it, the two fields are going to go together because they're the same physical tool. It's just a new offset. So, I mean, I could keep on doing this right up to 9 times. Now, once you start creating edges, if you want to delete an edge, you don't want to use the delete tool because you're going to lose the whole tool. You just want to go to Edges, and there's a delete command inside of it. And now you see we deleted the 2 or the 3. Now I'm going to delete the 2, and now I'm back to 1 edge. So in this case, I created the new edge, but then I came over to the field and hit my select key and then picked a whole new type of tool because initially it's going to obviously make it as a drill again. I don't want to treat it as a drill. I want to treat it as a boring bar. So I came in and said it's a roughing tool now. Pick this orientation. That updated the picture. So like if I was doing this tool right here, I did a new edge. See how it initially makes it with the same type. But if I select, I can pick a boring bar orientation. Now I just turn this tool into a boring bar. And you build it from there. And now that gives you the same parameters you're used to in what we just saw on the other tools. So the nose radius of the tool. What is the relief angle? This is a straight one. So I want to use 90 degrees with a 90-degree insert. What is the IC diameter? Usually these drills have some pretty small inserts, so I was using a 1/4 of an inch IC. And that builds the tool. Now when it's time to physically use the tool, here we have a quick little ID program. So first logical thing would be drill a hole, right? So I'm going to go in, and I'm going to select to drill a hole. And the big thing here is I just want to make sure I pick the appropriate cutting edge, because the cutting edge, when I select it, is what's going to go and fill out this D number. And a lot of us kind of never paid attention to the D number because I was only ever making one cutting edge. But once I get to, let's say, the ID turning operation, and I go select the next one down, it automatically fills out the cutting edge to be number 2. What's going to really happen when I run this? It's going to go in, it's going to bore that or drill that hole, and it's immediately going to start turning it. It doesn't have to go back to any tool change positions, anything like that. So the rest of the operations is going to be very traditional as to how I would have seen myself build a turning operation. You know, feed rates, depth of cut, material for a finished cut, that kind of stuff. But now, as I start to look at it and I simulate it, you're going to see that we'll be drilling and boring with that same tool. Now, the picture itself is going to update the type. So I won't see the back half of the drill. It wouldn't keep the drill up there per se. But it's physically the same tool. So no tool change would have occurred between the two operations. It would have just changed the D number and continued on cutting. And there we go. A simple little drilling and boring with the same tool. And you can start to get pretty creative with those cutting edges. A lot of times I'll use them with grooving tools where I want to hold maybe an offset from either the leading edge or the back edge. So I might create, you know, 2 or 3 different cutting edges for grooving tools. You can use this certainly for gang type of tooling scenarios. So let's say you got a turret, but you have one tool configuration that maybe has a couple different heads on it, like a turning tool and a threading tool, all built on a modular block. You can buy those. That would be an easy way to jump between those little stations. And now all of a sudden you took your 8-position turret and gave it an extra 2 tools. So you can start to certainly get very creative with this whole mechanism. Okay. So the next scenario, and getting into our first live programming example, is going to get into contour turning with pockets. And why I want to explain the tooling first is the tooling's directly in relation to this type of geometry. So as we go in, we're going to grab a couple different tools. You're going to see as it machines, it's going to be diving this tool down into different areas and using as much of it as it can, but it's going to leave then material there. And the amount of material it leaves is totally dependent on the values I gave it in that previous setup of the tool. So for us, we're going to go in, we're going to create a quick contour, and we're going to draw this irregular shaped contour, this pocket style contour. Once we do that, we are going to go into a stock removal, and one of the first things we need to look at is the relief cuts field. A lot of us are probably used to leaving that off, but that's what triggers the system to be able to do this type of contouring. And then we're going to start to see the gouge detection function. And when I say gouge detection, it's that tracking of the back edge. It's keeping the insert from gouging into the part. So we'll see here, I'll use a big 80-degree diamond strategy, and I'm only going to get a little bit of the part machined. Then maybe we'll jump to a 55-degree tool, and we're going to get a lot more of it machined. From there, the next logical step will be, well, how do I handle getting the rest of the material out? So at that point, we're going to then transition over to what is an option within the software called cut residual stock. So that may or may not be there, but certainly can be added. And then that's a quick little routine that allows us to then go in and tell it, hey, go figure out where the previous tool couldn't cut, and they'll cut it with a new tool. So we're going to get a chance to use that. And then we're going to get to simulate it, and you'll get to see the tool will now come in, different configuration, but just start machining where the previous tool didn't machine. Okay. So if we jump back over, I'm going to jump over to Program Manager, and I'm going to start creating a program. So I'm going to bring up the part print for us here. So this way, you guys can kind of keep that in visual, so you can kind of track or imagine what we're really machining here or creating here. I'm going to tell it I'm going to do a new program, and I'm going to call this I don't know, test 1, for lack of a better name. I want to be in ShopTurn, so I'm in conversational. I'm going to say OK. Now, you'll notice I'm going to jump over a lot of these fields because they have been certainly covered in lower level seminars. So if you don't know all these fields, I would strongly suggest taking a look at one of my other ShopTurn webinars. So we're just going to put in what's critical here. So obviously, this is going to be some rough stock. Let's say this is coming from bar stock, and I can use a 3-inch bar stock. So we're going to come down to our XA diameter, and this is going to represent our stock. Excuse me, I didn't have my number locks on. And I'm going to tell it a diameter of 3. So we give it 3, that's going to signify, now this blank, remember, is just for graphic purposes, representing a bar. Do I have any material in the face of the part? I'm going to say in this example, I don't. We'll say that we're just worried about machining this diameter, boss, then out and around the shape. An overall length of the part, and then how much it's sticking out of the chuck jaws. So this part, overall 6 inches, I'm going to say it's maybe sticking out 6 1/4. But we're just going to concentrate on machining this portion of the shape. Then my retract, all the same, so I'm just going to use a simple incremental retract of 100th on both axes. Atypical tool change position, so we'll just leave this alone. And my safety distance, we'll leave it our 50th thou. So I fill out the page, we hit accept, and now we're going to want to go in and we're going to create a contour. Now the name of the contour, as in the past, doesn't really have any bearing more than it's just a reference for you. So if you know you're doing multiple contours, I may start naming them with a number. You don't want to always have the same name, can't be duplicated or they'll get linked. But then I start building them from here. So my first scenario, I'm going to trigger a start point. So I said I'm starting out at the 1-inch diameter, and I'm starting right at Z0. If I had a chamfer here, I can handle that with this transition to start, contra start. I don't, so I'm not worried about it. So we'll just simply hit accept. So now, as we've done in all the previous examples, we're going to draw this shape. So my first move is going to be a Z move back. And we're coming back into -1 inch. Once we get back, we're going to pull her straight out to a 2.5-inch diameter. So we'll give it the 2.5 inch. We do happen to have a chamfer here of 125. And we want to accept it. Oh, I didn't realize you guys don't see my print. Excuse me. I just saw that. Let me share the print. That probably looks a little better. Okay, sorry guys. Off my game today. Okay, so I started at this front center of the part. I machined back on the boss of the hub. I machined out. I'm right here. Once I get there, I'm then going to come back, and we're going to keep moving around. So I'm out at the 2.5-inch diameter. I got my chamfer. Oops, went too far out. Now I'm going to move back. In this case, right off the print, I'm going back -1.5. Once I get there, we're not putting any kind of chamfers, so we're going to accept it. Now this is where things start to change for you. Here, I'm now going to start to dive back into my part shape. But again, I'm going to just concentrate on actually giving it the true geometry of my part. So if I look, I'm coming down to a 1.5-inch diameter. So I'm doing an angle move with the X down to 1.5. Now, dimensionally, I know that this is a 1/2 inch back off the other surface. So I could tell it, go to -2. It's easy to do the math. Or maybe the numbers weren't quite as simple. You can toggle to incremental, and I can say, hey, just go another 1/2 inch, -0.5. So sometimes, depending on how the print's laid out, I will go in and jump things to incremental as opposed to absolute. So we have a typical radius blend across the part of 250, so we're going to give that our 250 radius. That's going to put me at this first slope. I'm pulling over to a Z of -2 3/8, looking at the print. We got another chamfer. Now the default is always chamfer, so when I have a radius, I have to toggle it. Comes across. I'm going to do the X because I'm coming down. I'm coming down to our 1-inch diameter, same as the hub. I'm going back again, another 1/2 inch. We got another radius of 1/4 inch. So we start seeing it starting to look like the print. Now I'm going to go back to 3 7/8. Right. We got another radius here, most likely blended. Okay. We'll come out. We're coming out to 1.5 inches. I'm going back. Again, my 1/2. And we're coming to a radius of 1/4 inch. Straight back. It's going to get us to the back shoulder to 5 1/8. No transition. So for all intents and purposes, a square corner. So it'll just put the radius of the cutter in. Now I'm going to pull out to my final 3-inch diameter. Now, what a lot of guys don't realize, if I don't need to come across this top surface, but I still want to put a chamfer in here, a lot of us are used to doing an additional move across the surface just past the chamfer, but you don't actually have to do that. I can actually put a chamfer on my last element of my geometry. But what you do is you have to go now to the end field and see how it transferred the chamfer in. So when I edit this, like in the start element, I can then tell it the direction I have to move that chamfer in. And of course, if I pick the wrong arrow, once I hit accept, I'll see the chamfer won't either come up or it'll show the wrong direction. But you can do end of chamfers. You just got to remember to go into this little end field and edit that. So once the shape's created, I'm now going to, just like I traditionally would, go into stock removal. We'll go pick a, maybe that CNMG, that 80-degree diamond we created just before. Give it some feeds, give it some speeds. Here I'm going to We'll run, I don't know, 500 surface feet. Now I'm just going to rough for now. I don't want to rough and finish. I'm going to take 100 thou per pass. We'll leave, say, 10 thou and 10 thou. And I want to just make sure that I don't have any additional stock. So that's saying that this field right here, when I'm on cylinder, is saying that the stock is gauged by the shape I just drew. But I'm not going to turn on relief cuts yet, and watch what happens. So if those are left off and I simulate, the system's just going to kind of blow right by that shape. Retraction plane, that's fine. Machine, well, what I do? I'm talking here, and I'm not paying attention. Tracks should have been all right. Oh, I'm on an inside. That would be a problem. Okay, sorry. Catch back up again real quick. So we're going to start to machine the part, but she's going to blow right over the pocket. So here you'll notice it's not even going to enter. And this may be an appropriate strategy. You know, even though I drew the whole shape, since that tool doesn't have a lot of relief, I may not want it to even try to enter it. But if I do, I have to first trigger it by turning on relief cuts. Now, when you turn on relief cuts, you do get the ability of changing the feed. A lot of times as it dives into material, you want to maybe reduce the feed. Here we're virtually machining, so I'm not that concerned. But now we're going to start to see why it's so important for us to know the back half of that insert. So if you watch, this tool is now going to attempt to get into this shape. And the amount it's going to let it go in, see, we get this, I'm going to zoom in a little bit. See, there you go. So I get this nice tapered wall. I'll just bring in the full view. Graph's a little better that way. All right, so I'm coming down. So that's obviously not enough to handle machining this part. Certainly I could change tools and do a lot of residual material, or most of the time I'll then choose maybe the appropriate roughing geometry based on this first op. So, you know, maybe instead of using that tool, maybe I wanted to pick a 55-degree tool I had in my library. So immediately with this new 55-degree tool and this oriented angle of that insert, I can start to see how much that tool will get me. So I come in, starts machining, and you can notice now with the back side of that tool, once we get there, it's going to get me a lot closer to the orange line, which is the finished geometry that I'm trying to get to. So this would probably be a viable, a little more accurate scenario for machining this part out. But I do now have to handle this material, and that's where things could get a little trickier. So this is absolutely where I want to then show you what the residual material is all about. So what this cut residual button, and if you have the option, the button will be here. If you don't, it'll be blank. It could be added. This allows you to now go pick a unique tool. So I'm going to use a handed tool that's the opposite direction. So in this case, I was machining with a left-hand tool because this is a rear turret machine, but I want to now put in a right-hand tool to kind of back turn this scenario. The rest of the parameters are really the same that you would be used to using, you know, depth of cut. Now I will warn you, you want to make sure you transfer the correct finish stock over here because you'd want to have the same amount of material there for a finish. I do have to have relief cuts on or it won't dive in. But now the system will automatically look and say, okay, let me figure out where the last tool couldn't fit, and I will then go in with that tool and machine just those areas. So we'll rough it out. Here we'll come in. Voila. So remember, we still have our 10 thou of finished material. So to complete this part, I would most likely then go back to my standard stock removal, pick an appropriate finish tool that would finish the entire geometry. So I'm going to use a 35-degree left-handed tool. I certainly want to change this to a finish cut. Now, make sure you keep relief cuts on, or if they weren't on, put them on. That'll make sure, like you can even see in the image, if I shut this to null, it wouldn't go into that area. And now I'll get my final operation. We'll have a completed part leveraging residual material. Later in the webinar, we're going to briefly look at the other lower grooving and plunge turning ops. Both of them have the same functionality with residual material, and it's just one option. So once you get residual material, you have it, it's going to give you a 2 for all 3 of the cycles, certainly the turning, as well as the grooving and the plunge turning. Okay. So the next area we're going to explore in this webinar is cutting feed strategies. So there's a couple unique strategies here that I like to point out because a lot of guys don't realize what they do. And first things first, we have what we call intermittent feed. And intermittent feed is kind of like a pecking cycle for turning. And what it's there to do is it's there to give you a chip breaker when maybe the chip breaker that's on the insert isn't sufficient. You know, a lot of your nastier materials have a hard tendency to want to break. Titanium, zinc canals, some of the stainlesses, certainly your plastics definitely don't like to break. So what we can do is if we use the little DI field right here in the cycle, that gives us what we call an intermittent feed. And this value is a linear distance, and it's saying every time I've gone that distance, I'm going to break my chip. Now how it breaks the chip is she's going to potentially dwell and back up, and those values are directly related to a couple machine parameters. So these are the 2 machine parameters that control the motion. So to see what that looks like, I just have a little video staged for you, and if you watch the video, you're going to see the tool backs up. In this case, it looks like I'm backing up about every 1/4 inch or so. Now, the backup is new to operate. The older system would just pause just long enough to break the chip. And again, if I don't want it to back up, or I want to control how much it backs up, or how much maybe it delays prior to backing up, that is all done again from these 2 machine parameters. So the 55,585 and the 55,586, I can control the nature of how that responds. But you find this is an invaluable cycle when you get to carriers that I just can't break that chip. And then, you know, you can obviously play around with how aggressive this value is, greater or less than. Now, another field that is absolutely overlooked, and for those of us that get into machining a lot of the nastier materials, there's this condition that occurs called insert notching. And insert notching is a characteristic that will occur, or a condition that will occur, up the insert at the point in which the rough stock is physically hitting the insert. So, you know, like if I'm taking a depth of cut of 100 thou here, and that's a radial value, so this is an actual amount of depth of cut. If I was to measure from the front edge of the insert back up 100 thou, that's the point at which the stock is hitting. Just like you see this little arrow on this insert right there. So over time, hitting at the same point, you'll actually get more wear at that point than you will at the cutting edge, and it will cause this insert to prematurely fail. So your leading edge insert, which everybody always thinks of as the area that's going to break down the worst, isn't necessarily the actual portion that causes the insert to fail prematurely. And you can even see I have a little picture here of an actual insert that's showing you a heavy chip notching that was occurred. So what we've done is we've created a function called variable depth cutting. And that's triggered right here by these little icons. So this is where we guys always miss. Usually they have this second icon here set to an equal depth of cut. But there's a way to set it up. If you toggle it to a varying depth, and what it does is it aligns the depth up to some features. That gives you this third field. Once you do that, you can control the variable. So what is the actual cutter path going to look like? Well, if you look at here, the tool is going to come down, and now you're going to see that first cut's actually an angle, and then I'm going to get a straight cut, and then I'm going to get an angle, and a straight cut, and this is your varying. So now it's changing that tangency point on the insert. Now you may get an extra cut or two depending on how all the values stack, but you're going to dramatically increase, especially if you're experiencing this type of wear on the insert. It's going to reduce that potential. Now, certainly how much it backs up, that's controlled by this little parameter right here, this 55,583. So it's a percentage number, and really what it's saying is based on my depth of cut, I'm going to back up that percentage of it. So if I have 40%, it means it's backing up to 40 thou. If I had 50, back up to 50 thou. You guys kind of got it. So I can control how aggressively this is. You know, you might want to have it just shallow enough that's just slightly changing it. Maybe I'll have it to 20%, let's say. So that can be a couple different areas. So just to show you real quick here on the same program we just created, how to get that little trigger. It's all right down here. So initially, you're probably used to this being a constant depth of cut. So if you want the variable cutting, the first thing you need to do is toggle that, and this is going to toggle to the align cutting edges. So that's going to say that it will truncate a cut to align with certain features. And then you can still have straight cuts, so it's not using the variable cutting, or now that you get this little parameter, you can toggle it, and this gives you a variable cutting to reduce that insert shipping. And just accept it, run it, and there we go. Okay. So for time's sake, we're going to move on, and we're moving on to our next operation, which is called turning for irregular stock. So this could be handled in two different ways. You know, maybe it's a pre-machined part that I need to then rough it because it had some other operations down a little more, but the part is no longer a cylindrical type of shape. Maybe it's a cast part like I see here, and I don't want to have all these dead casts in the air. Well, the system has functions to be able to handle that right within the conversational programming. So what we're going to do is we're going to take a look. For time's sake, I'm not going to draw the entire part, but we are going to kind of dissect and put it together a little bit. So this is going to be the part we're going to use for an example. And it's got a little bell shape. What we'll do first is we'll assume that this part has a consistent value of stock around it. And then after that, we're going to actually even physically draw the stock. So the way it'll work is we'll come in, we'll draw it just like we draw our other ones. We'll create a contour, create a stock removable, and then we'll use the strategy called allowance to do our first machining up. And what allowance will do is it'll say, okay, I'm going to put that amount of material on the entire shape and just machine those areas like we see here. Just going to kind of run down and just machine those areas. After that, we're then going to explore drawing the irregular stock and how that all kind of links together. And we'll build that in. We'll have our finished part as we did before. We go into stock, but now you need to trigger this to contour. And that's what contour means. It says, hey, the stock I'm looking for is coming from a contour, and it has to be part of this chain. And you always want the stock to be first, then the finished part, and then the cycle. So here you'll see the cuts amounts will now vary based on that shape that I drew for the stock, as opposed to always being kind of stuck in saying, well, it's got a half-inch of material where maybe it doesn't on the front, and maybe it doesn't up top. So you can get a much more optimized cutter path if you take the time and draw the stock. So what we have here is I have a little sample that, no, not this one, that I was creating before. And what we're going to do is, first things first, we're going to set this up as if it was just the basic routine, right? So we'll have come in, just like you saw before, it's normal, you know, draw the shape, right? So I'm going to start at 0, 0, because we're going to base off the part, and I'm going to draw this little bell shape. So again, to refer to our print, this is our little drawn shape here. So now what you need to do, just like you did before, is you're going to associate it to a stock removal cycle. But the stock removal cycle now, you're going to come down to BL, and BL is representing the stock that we're machining from. Your blank description is the B for the BL. And we're going to toggle this to allowance. And allowance now gives us an X and a D value. And that value is how much material I'm adding to this surface shape. So here, I'm just going to say, and it can be a different value. It doesn't have to be the same, but it will be the same for all X surfaces or all Z surfaces. I'm saying I got a 1/4 inch of material on each of these two surfaces. Now, I don't have any relief cuts because I'm not dropping into any pockets, so I can leave them off. We accept it, and now you're going to start to see this optimized cutter path. Now, the stock that you set up in the header page only supports a blank. So you're going to understand, obviously, in your application, that's not there. So we're going to kind of negate the fact that it thinks it's machining through a bar per se. A lot of times what I like to do in this example, I'm going to zoom in here for you so you can see it a little better. But I may not look at the entire side view. So a lot of times I'll put it to the half cut view. So then as I simulate, I don't lose the insert. I get to at least visually see the insert the whole time so I can better understand what the actual cutting strategy is going to look like as it drops down through. Machines through the part. So here, this is a perfect example of where potentially I'm getting some dead passes because I had to tell it I had 250 material in my Z, but maybe I didn't have it on the face of the part. So if I want to then change this around a little bit and I need to add some kind of stock, I do have to draw that stock. So what we're going to do is we're going to just add a drawing. We're going to quickly draw this irregular stock shape. And I'm just going to use this little detail to give me some rough dimensions to draw the stock. So I'm going to go over to contour. I'm going to do a new contour. Oops, typed the wrong button. New contour. And I'm now going to tell it, and I'm just going to use the name stock for my own reference. The name doesn't trigger this. It's the order of operations. First one's going to be the stock. Second one's going to be the contour. Okay. So we're starting to draw the shape. Where do I start? Well, stock's starting from dead center, 0, 0. Stock pulls out. So here, this is a radial dimension, so I want to make sure I go out to 2.5 because I'm telling it incremental or absolute. Or I could set this to incremental and put that value. We're going to move back in my Z. Oops, I actually did a boo-boo here because the start is not 0. The start is 1/8 out. So let's get our 1/8 in the positive Z. Okay. So we pulled up. Now we're up at this corner. I want to move back in. I'm going to move back in 1/2 inch. All right. Accept it. I'm going to pull out. I'm going to pull out to a diameter of 4. Now, on this little part, I don't know where the end of this Z move is. So I'm going to leave it blank, but I am going to tell it the direction I'm moving in. And this triggers our trig help functionality. So whenever you don't know something, leave it blank, accept it, and then start drawing beyond. And if your numbers start to stack, things will start to automatically kind of fill in. So here, my next move is going to be an arc. So I do want to go into an arc event, tell it my direction, give it a radius, give it an end point. So the end point is going to be out. Well, this diameter I know to be 7. And then we got another 3/8 per side. So I'm going to 7.750, right? I'm coming, if I know this back edge in this print is 3.5, left's 1.25, I would be going back to minus 2.25. Just do the math real quick. The center of my arc, let me give it, because I know it, assuming that it's even with the top point, and voila, I start to get an arc. So this is saying, is this the appropriate arc you want? There might be 2 different solutions. That's where the dialog select comes in. So you want to make sure you pick the one that's going to look like your print and accept it. And now what happened was not only did it fill out the rest of the information here, but it also calculated what that previous move would have been to have intersected this arc. That's obviously not tangent to that move. Okay, so we're going to finish up the shape. So I'm going to move back to my minus 3.5. And this is probably one of the biggest things that messes guys up. You guys are used to just having to draw the part. But when it comes to the stock, it has to be closed. So I'm going to move right down to 0. And then I'm going to use the close contour by expanding the buttons over. It brings me right back. So you do have to make sure you close your stock shape. If you don't, it'll give you alarms. You won't be able to use it. But that's it. Just draw whatever the stock is. It'll automatically signify that and calling it the blank, calling it the finished part, just by order of operations. It did this. Remember, I named it here, but it created those. And I just want to make sure I come in now and switch this to contour. Once that's triggered to contour, if we simulate it, we're now going to see that we get an optimized cutter path based on that drawing shape. So now I can just control a little bit more where I'm spending time cutting and certainly where I'm not. So now we see it's just going out beyond that yellow line. That's certainly signifying the stock I drew. And now I don't have those big cuts in the front because I didn't start all the way out at 250. Okay. So this is certainly how I would leverage the irregular contour functionality. And, you know, certainly it's going to be up to you based on whether I have to go through all the steps of drawing the contour or if the allowance is sufficient, shall I say, sorry, for the part geometry you are now currently cutting. Okay, so where do we go from here? All right, the next area in the more of the advanced world, I did mention that I wanted to just touch upon the contour grooving and the plunge turning events. So what's nice here is we have two cycles that will give you a very different cutter path solution than the standard contour turning functionality. And when it comes to the grooving, what it allows me to do is allows me to draw any shape I want. So if I have any weird odd-shaped groove that maybe don't fit into our standard grooving cycles under the turning button, I can still do them. And I'm going to do it through the contour turn function. So using the grooving and using the plunge turning, which we'll get to next, is the same mechanism as I've used in the past. So I'm going to come in, I'm going to draw the shape. So the shape has no idea it's going to be a groove or whatever. But then, instead of going to stock removal, I'm going to go and select the grooving routine here. And I'm going to insert a grooving cycle that's going to be linked to the contour. And now it's going to give me more of a grooving cutter path. So I will be coming down in the X, machining that part or machining that shape. The end result here, as we're going to see when we go to simulate it, play around with it a little bit, will certainly be this, this grooving geometry on any shape. And you can really use it on absolutely any shape you want. Certainly it may not be the most proficient method, so a lot of that's going to depend on the part, but it is there for you as an option. Then from there, the other one that's pretty nice is what we call plunge turning. Now the mechanism works the same. I'm going to create or draw the physical shape that I want to turn. But then I'm going to go into the plunge turning event. And with plunge turning, also known as like bidirectional turning, the system's going to machine across the part, feed in, machine across, feed in. So it's trying to reduce the total number of rapid moves. Because if you think of standing turning operation, every time I come off that part and wrap it back to the start, that's lost time. That's adding cycle time without cutting. Certainly you have to be aware of the tooling you go to use. Not all grooving tools, actually most grooving tools do not like to side turn. So there are specific tools that the cutter manufacturers have created that allow you to do this type of operation. And they usually refer to them as groove turn tools. A lot of them are like a dog bone style insert. Those will work quite well in this type of scenario. So you'll link it to it. We'll fill out the page. We'll talk about some of the parameters, a couple different unique parameters here. But now we'll see a much different cutter path, even from that grooving cycle. So I've pre-created, just for time's sake, I've pre-created these two different routines for us. So we have the grooving routine first, and in here, same as we've seen in the past, I'll have come in, I'll draw the shape. Now in this one, I wanted to use the initial chamfer routine first. So on my start position, I did tell the system that I had an 1/80th chamfer in the direction. Then I came around, drawing the whole part, and here I dropped straight into the groove, straight across. So I didn't have to, jump over it because I was going to groove it with some other different tool later. And we also did the end chamfer like I showed you before, but just remember when you want to do that, you do need to tell it the direction in this transition to end, to contour end, so it knows which way to blend the chamfer to it. But once you've built it. Now under contour turn, you want to go to the grooving. Now you'll notice you also have the residual buttons here too, like I said earlier. So everything we saw in cut residual would work the same way here if I had a scenario where there was material being left over and I wanted to use a different tool. But the way it works is when I go into the grooving, I do need to pick an appropriate tool. So I would use what we call our plunge cutters or our grooving tools to kind of build one real quick for you. I would come down, I would select new tool, and we would pick a plunge cutter. So a plunge cutter is always going to represent some type of a grooving tool for us. So pick the orientation. Now what's a little more important when you're doing this is paying attention to the little indicator here to the left of the insert, and that's defining where you would touch that tool off. So if I was using this OD grooving tool, I'm touching it off to the left edge of the insert as opposed to touching off to the right edge of the insert. And then you can see you have all your 4 potential orientations, so it's a total of 8, just like the other ones. So I'm going to use this first position, select OK. We're going to say this is a plunge cutter, and we're going to say that this plunge cutter is a 200th thou wide, just for my own reference here. The lengths would get filled out when I touch it off. Certainly I'd need to know the radius of the insert. Traditionally, grooving tools have a much sharper, smaller radius than they would traditionally see in a turning tool. The width of the tool. So that is the physical dimensional width of the tool. So if I was to send it into a part, what kind of groove width would I get? So I said it's a 200th thou, so I'm going to type in 200th thou. Now you don't have any relief angles or anything here because it knows that it's a rectangular type of geometry, but you do need to go give it the length of the insert. And the length of the insert's not that critical. It's really just for the graphic representation of it. So if I tell it it's a length of a ½ an inch and I send that grooving tool 1 inch deep, it'll let it go. We're not limiting your depth based on this. This is just to kind of create the picture of the tool more than anything else. It doesn't have a lot of other bearing on the part program. But I build the groove tool. I tell it to the program. Now we're going to give it some feed rate, just like we normally would, an RPM or surface footage. Am I simply roughing? Am I finishing? Am I rough and finishing with the same tool? Pretty common with a grooving tool. What would be my finish feed rate now that I am doing a finish operation? I do need to pick where the groove is oriented. So is it a face or is it a turn? Is it an outside or an inside? That's up to me. And then I give it the peck amount. So as I start grooving this, how much do I want to feed in, advance in the X until it breaks its chip? So 1/4 of an inch, 1/8 of an inch, what I want to do. How much material do I want to leave for a finished cut? You want to be conservative here, especially on grooving tools that are traditional grooving tools, because they don't like to take a big side load, so you'll find yourself putting a smaller value than you traditionally would with turning. We do have that same intermittent feed like you saw earlier, so it could be leveraged here, but normally you don't need it because you're already doing a peck there. All of the things I just showed you with the contours and the allowance for the stock could all be leveraged in these cycles the same way. But I fill out the page, I hit accept, the two are linked together, and now we're going to see a grooving cycle. So in a part like this, this certainly would not be the most proficient method for machining the part, but depending on the geometry, it could be. If I knew that there was a straight feature up here and back and this was a groove, well, there might be too much area that I'd have to flip between right-handed and left-handed tools, that the little bit of cycle time loss I have here would potentially still be quicker. So that's where you got to kind of play with how you leverage it. But boy, when you're getting to strange irregular shaped grooves, it is just an awesome cycle to be able to leverage. So we see it here. It's working down through. That's the peck, 1/8 inch peck I did. And there's the finish. Finish, finish. So it's trying to kind of figure out its best strategy for how to finish based on if there's a wall there or not. And that would be our grooving cycle. Now, from there, we also have the plunge turn. Now, in the plunge turn, it's going to draw the same exact same shape. But here I'm going to pick, under Contour Turn, I'm going to pick the Plunge Turn button. And now I'm going to use the same type of tool, but you do have a little different fields. So I can control the feed in the X as well as the feed in the Z. Because remember, it's going to come across and then it's going to advance in the X. It's going to go across and it's going to advance in the X again. So I may want to do a more conservative plunge feed than I would cross feed. Certainly surface footage, roughing finishing, the feed when I am finishing. The depth per pass here, that's going to be side. So this is more traditionally like a turning operation. So I'm not pecking down here. I'm actually side turning with this cutter. So a lot of times you do tend to take a little less aggressive a depth of cut with this type of tool. How much material I want to leave for a finished cut. So all this stuff's all the same like you just saw. But as you fill it out and you accept it, now the end resulting cutter path, however, is significantly different than what you just saw. So now it's going to feed across, down. Now I want you to kind of look at the little bit of the dance it's doing at the ends. It's actually backing off a little bit, and I can slow that down. We'll let it finish, and we'll zoom in. And maybe we'll put it to the full side view. And let's just slow it down here a little bit. So what happens on those tools is as they're machining across, they're actually deflecting a little bit. So we pick the cutter up at the very end to keep that blade from springing back in and gouging or overcutting. So there's a lot of stuff going on here. These little nuances that the cycle automatically takes into account to give you an accurate and viable cutting solution. So it's pretty cool cycle, and certainly much more efficient. I mean, you can see how many less rapid moves we get here. Okay. So with that being said, we are winding down to the end. I did want to give you guys a chance to open up the floor for some potential questions. Just like in the past, if you have questions either on this content or maybe on some other content, feel free to share it. We'll use the Q&A panel there. It should be in front of you. If you don't see it, click the little Q&A button there, and you can just type your questions in, and we can take them from there. Okay, so I'm just browsing this now. Okay, so we got a question in. How would it handle form tools or tool definition, cycle types, etc.? The one thing we don't support at this point is the ability of creating irregular tools. So the tools themselves do have to be in our library. You can certainly use a form tool. The downfall certainly is there's no cutter compensation associated with that shape of the form. So I do a lot of form tools, but usually you find in a case like that, you're probably just doing a much more simple type of cutter path, like a plunge and whatnot. So it's going to be up to you to realize that it will physically, you'll machine the right geometry, but the graphics won't necessarily know. So hopefully that answers your question, Jason. All right. There's another question came in. How do we get residual material? I'm assuming this would be a scenario where somebody doesn't have the button. Licenses in the control are actually pretty straightforward. They're pretty simple. The way that whole thing works, it's either something that a basic dealer can do, or you guys as an end user could even do. The way it works here, and I'm just going to jump over to the simulator real quick. Under the setup feature, there is a button called licenses. And what happens is your licenses are linked to a unique serial number on your machine's CF card. And what happens is when you get a new license, we spit out this new number, and that automatically activates that software license because the functionality is already in the control. So it's not like we have to install software or anything. And then what you do is you would go to the appropriate option. So you would find, in this case, residual material. See if I can find it real quick. We got lots of options, but a lot of this stuff is for real advanced kind of stuff. But here's the one for residual material detection. So if you don't have it, you'd find that both of these boxes would be blank.
You purchase it from us. Not a very expensive option. I mean, I don't want quite off the top of my head, but it's certainly less than $1,000. But you would physically get the option. You purchase it. We send you a number. It's unique to that option. You go onto a website. You type in that CF serial number I told you. You type in the option number, and it regenerates that number. You can physically type that into the control, and then the gray box will be checked. So for you to activate it, you then only have to come down to the white box, hit the select key, a little checkbox will be there, reboot the system, and then from there, those buttons will automatically appear. You know, options like that don't require any type of commissioning or setup, so they're really quite painless to turn on. There are more advanced options that do get a little more involved. Then you probably need to get somebody involved in it. Is tool orientation in the tool list still the same regardless of B-axis orientation? So I am expecting that you're referring to B-axis on a B-axis style lathe. It is. However, the one thing you got to be aware of when you get on builders' machines like that, when they get into more of the 4- and 5-axis orientations, is they'll have a base position of the tool that's going to match the tool offset geometry. So this little indicator right here. So you kind of got to know, you know, where are they saying the base offset is? You know, is it the insert, a standard OD turning tool? Is it with the insert pointed to the left or pointed down at the part? Because now that you have a B-axis rotation, you can swing that tool around. Those are pretty cool machines because not only can you swing the tool around, but they're usually on a spindle, so you can flip the tool upside down too. So I could take the same cutter and I could do really ID facing operations, OD turning operations. I could flip it upside down and do back turning on a sub-spindle. But yes, the orientation is the same. You just got to know where your base value is when you're picking the correct picture. But the one thing that's usually always a good indicator is, like I was saying in the beginning, that first field should always represent an OD tool. So if it looks like it's pointing the other way, that's how they commission the machine. So hopefully that answers your question, Tim. Okay, let's see what else we have. Can regular stock work with a DXF? It can, absolutely. We'll certainly be getting into DXF, as I mentioned, the next up and coming, because there's an additional piece of software you use to leverage it. But yeah, you can have multiple contours in a DXF and then pick those features, and then it'll come in. Now, it doesn't necessarily know it's going to be stock at that point, so it's going to be up to you to kind of order the shapes, because when you first bring in a DXF, you're just going to have a default program created with a couple shapes. But yes, you can have DXFs for the irregular stock. Let's see what else we have. Here we go. There's another one. Can we get a copy of the PowerPoint for the insert descriptions, etc.? Absolutely. I would say probably the best thing for you guys is anybody that would like a copy of the PowerPoint, just give me a quick email. Everybody should have my email address, but if you hadn't recorded it, we can. I can just run up right to the beginning here. Bear with me. Shoot me an email. It'll be a little easier for me then to try to send it out to everybody that's on this call. But if you shoot me an email to the chris.pollock@siemens.com, I would be happy to share the PowerPoint with you. And looks like we're in good shape. So if everybody else is good, I am going to end the recording here. One second.